Hello everyone again. Let's talk about circles. So this is grade 10 academic math, lesson number 5. So this is our last little lesson on analytical geometry, and it's all about the mathematics of circles, how we can actually deal with circles in an analytical way. How can we come up with equations for circles, and how can we do some math on circles? Okay, so what is a circle? So we've all know what a circle is from kindergarten probably, but in a mathematical sense, a circle can be defined by the set of all points at a distance r from a point O. So we have our origin O, and the circle is defined by the set, so this infinite set. So this line that makes up this circle is actually a smear of an infinite number of points that all satisfy the condition that they're a distance r away from O. Okay, so really when we think about lines from a geometric sense, they're an infinite set. It's a set of all the points that satisfy some sort of condition. So that condition can be y equals mx plus b, or in this case, it's going to be something about the radius r, this distance r away from that, that origin O. So what we're going to do is we're going to take this circle and we're going to stick it on a Cartesian coordinate system again. And we can do some mathematics looking at radial arms and this sort of stuff. So let's take a different example here. This is a circle with a radius of 4. So as you can see, it has an intersection here at what's that, 4, 0, and then another intersection here at 0, 4, and then an intersection over here at -4, 0, and then an intersection down here of 0, -4. So we can now construct a radial arm that can be at any angle, anywhere around this. I just arbitrarily chose this radial arm. Any radial arm will suffice. And once we've done this, we can use our coordinate system, our x and y that we've defined here, to come up with a triangle. So for us to go from the origin here to the circle point, let's call this point P or something. For us to get there, another way you could get there, instead of traveling along r, is you could travel a distance x along the x-axis and then a distance y vertically to get there. Now notice this is a right angle triangle, so we can apply the wonderful Pythagorean theorem. Right, c squared equals a plus squared plus b squared. We know that c is actually the radial arm, the hypotenuse of our triangle, and the legs, a and b, are x and y. So let's replace those. So r squared equals x squared plus y squared. And there you go. Just rearranging it slightly, we end up with an equation for any circle. The equation for a circle is always going to be x squared plus y squared equals r squared. Okay, so in this example here, the radius, we said is 4. So I'm going to plug in 4 into the radius, and I square that, I get 16. So my equation for this circle is defined by x squared plus y squared is equal to 16. It looks a bit strange, I know, because it usually we want to put the y by itself, but this is what we call an implicit equation. The x's and the y's are sort of mashed together on one side of the equation. We could rearrange it a little bit. The problem with this that you'll see in grade 11 is if I try to rearrange this equation, let's say solve for y, I'll end up with 16 subtract x squared, and then I can take the square root of both sides, but a square root has 2 answers. And then we end up with some strange, we actually have like 2 halves. We have the top half of the circle, and let's not worry about that. Circles are strange in that it's not truly a mathematical, what we call a function. And I'm going into grade 11 here, so I'm going to stop and just carry on. Just know that x squared plus y squared equals r squared. That's the big lesson, the big idea of today is this equation here. X squared plus y squared equals r squared. So let's do a couple examples. So let's say we have a circle with a radius of 8. What's the equation going to be? That's pretty straightforward. You take our equation, our general equation, x squared plus y squared equals r squared, and replace r with 8. And then we square that, and we're done. X squared plus y squared is 64. Very straightforward question. What happens if instead it asks us to find an equation of a circle that passes through a point? So they give us a point on the circle, not the radius. They just tell us that this circle has to pass through this point 512. So very similarly, we're going to take our equation, x squared plus y squared is r squared, and instead now we're going to replace the x and the y with, in this case, -5 and 12. Okay, so we're going to square 5. -5 times -5 is 25. 12 times 12 is 144, sorry. And that comes up with 169, which basically is our equation. That's our r squared. So we can just directly substitute that into our equation there. Right, this is our r squared. So I can plug that right into there. And notice that this means that the radius is going to be 13. Notice quickly that this is another one of these things called a Pythagorean triple. There are 3 numbers that satisfy Pythagorean theorem and are integers. There's a bunch of them. Another good one to remember is 3, 4, and 5 is another what we call Pythagorean triples. 9 plus 16 is equal to 25. Right, that works. So there's not very many of them, but anytime we have numbers that satisfy the Pythagorean theorem and the numbers themselves are integers, right, there are no decimal places, we call that a Pythagorean triple. And this one is, right, this I chose this example so that we wouldn't have to worry about decimals. So let's try a bit more complicated question here. So let's say we have a circle with a center of 0, 0. So the origin is 0, 0, the middle of the Cartesian coordinate system, and it's defined by the equation x squared plus y squared equals 25. The first part of the question asks us for the radius. That's pretty straightforward. And part B here. So we have 3 points on the circle. A is 0 something. B is something 0. So there we have, this is going to be a what? This will be a x-intercept, and this will be a y-intercept. And then we have some general point. We're going to call it C. And there are points on the circle. It's asking us to determine a possible value to fill in each blank for each point. The point C must not contain any zeros in its coordinates. Provide calculations to show that the point lies on the circle. So now we're going to use analytical geometry to determine the equation of, C. Use analytical geometry to determine the equation of the perpendicular bisectors of the chords AB, AC. Yikes, what does that mean? All right, let's start with A, okay? Determine the radius. That's pretty straightforward, right? We know that r squared is 25, so r is 5. Right, we look at the equation x squared plus y squared is 25. Right away, you can say, oh, look at that. The square root of 25 equals 5, and we're done. Okay. Now, what about B? So I know that I'm going to have a 0 in for the x, and I'm trying to figure out what the y value would be for there. So let's replace in our general equation for this circle, x squared plus y squared equals 25. We're going to replace x with 0. And that just means that y is going to end up being 5. We can do the same thing with y, and we end up with x is equal to 5. So right away, we can figure out that's going to tell us our point is going to be for A. One of our points is going to be 0, 5, and the other one is going to be 5, 0. And that makes sense, right? Because we know that if we just draw a quick picture here, if this is a radius of 5, we know that this distance is also going to be 5. So this point here has to be 5, 0. And we know that since this radius is also 5, this will be 5, 0. Right, this makes sense visually. Algebraically, it makes sense too. Okay. For C, it asks us to find another point. But remember I said about that Pythagorean triple, 3, 4, 5? Because the radius is 5, I know that 3 and 4 are numbers that satisfy Pythagorean theorem nicely. I could have picked any number here, or any arbitrary number, but then I would have got a whole bunch of decimals. So to make my life easy, I chose 3, because I recognized 25 as being the square of 5, which is a Pythagorean triple number. So I'm going to replace x in this case with 3, and then I solve, right? 9 equals y squared plus 25. Subtract 9 from both sides, I get 16, and the square root of 16 is 4. So therefore, my third point is going to be 3, 4. Okay, it could also be 4, 3. Right, that one will work as well. Let's go quickly. Let's go to GeoGebra. I do not like that word. This is a circle with radius 5. Right, and you can see if I move this radial arm anywhere, doesn't matter where I go, I'm going to get these are the x and y coordinates of this point C here. But it doesn't matter where I go, the radius is always going to be 5. Right? If I square this number, square x and y, take the sum of those squares and take the square root, that's what this number here is calculated as. It's always 5. And I chose this number. I chose 3, 4. See if it'll let me do it exactly. No, it doesn't snap. Oh, there, it snapped. So as you can see, this number, 3, 4, satisfies the equation x squared plus y squared equals 25. Okay? So there we come up with that equation. Now, the next question is a bit more complicated. Let's go, what does the question say exactly? Using analytical geometry, determine the equation of the perpendicular bisectors of the chords AB and AC. Okay, so what does that mean? Let's go to that circle here. So we need to, this should be labeled A. Sorry about that. This is A, and this is B, and this is C. Can I change that? Ooh, label A. Will it let me? Come on, you can do it. Here, label A. There it is. Okay. Except this is labeled A. Let's change this label to O. All right. So we have our O. Okay, so we have to construct a chord. What's the chord going to be? AB. So we'll scroll down here to line segment. So we're going to make chord A to B. And it's asking us to determine the equation? Using analytical, the equations of the chord AB and AC. Okay, so this is AB. And then we can also go A to C. And it asks us to determine the equation of these two lines. Whoopsies. So this line here, let's color it red. And this one, let's color it blue. So it's asking us to figure out these perpendicular bisectors, the equation of them. Now we can actually use GeoGebra to help us. Perpendicular bisector of B. To make a perpendicular bisector, to make any perpendicular bisector, we can just go down to, there's actually a tool for that in GeoGebra. Yuck. Anyways, perpendicular bisector tool. So I'm going to click on the tool, and all I have to do is click on my line here, and bam, it has constructed a perpendicular bisector. And just by looking at this equation, I see that the y-intercept is 0. Sorry, looking at this line, I can figure out the equation. The y-intercept is 0, and the slope is, I go over 1, up 1, over 1, up 1, over 1, up 1. So the slope has to be 1. So the equation of the perpendicular bisector of AB is going to be y equals x, just by looking at this. Let's see if we can show that algebraically. Let's do that actually. Okay, that was just using GeoGebra to help us. So what are we going to do? How do we do this properly? Okay, so those are our 2 points for our chord AB. So we're going to take our 2 points, and we're going to come up with a slope of the original line, of the original chord AB. That's what I'm calling MAB. So the slope of AB, taking these 2 points, this is going to be my x1, this will be my y1, that's a y, this will be my x2, this is my y2, and I plug them in, and I end up with a slope of -1. That's the slope of my chord. To come up with the slope of my perpendicular bisector, I need to now do the negative reciprocal. So I take my fraction, and I flip it upside down, and I change its sign. So the slope of the line perpendicular to AB, that's what I'm saying here. So perpendicular to AB is now going to be 1 over 1, well, flipped is 1 over 1 still, and positive. So the slope is going to be just 1. Okay, so I know that I have this equation, it's going to be a line. I can replace a point. I can pick one of these points, A or B. Which one did I pick? I picked A because it has a 0 for the x. So then all of this will just cancel out. Anything times 0 is 0. So working this out. That's 1 second. Okay, so sorry. Then we're going to have to find a midpoint of the chord AB. So we're going to take our midpoint formula, take our 2 points A and B, plug them in, and we get the midpoint is 5 over 2 and 5 over 2. Does that make sense? 2.5 for each. Let's go back to my graph. Does that make sense? So this is going to be my chord AB. So my midpoint is here. That's going to be 2.5 for both x and y, which makes sense. So I'm going to replace those in my equation. So this will be my slope, and this will be my x and my y. And the only way that 5 halves can equal 5 halves is if b equals 0. And then I can substitute everything into my formula, right? Which is exactly what I got. Negative. Whoopsies. Sorry about that. So y equals x is my equation, which is what we expected, right? When we looked at this, we said that y equals x was the slope of 1, and the y-intercept is 0. So y equals x is our equation, and we showed it now algebraically as well. Okay? So let's do it now for the other chord. So this was the chord AB. So now we have to do the same thing for the chord AC, right? So this is through the points 0, 5 and 3, 4, which we just came up with. So we'll do the exact same sort of idea. We're going to find the slope. So we're looking at the change. So we went from 5 to 4. So that's a drop of -1. And we went from 0 to 3, which is an increase of 3. So my slope of my line AC is -1/3. Let's look at the graph here. Does that make sense? Yeah, I went down 1 and over 3. My rise is -1, and my run is 1, 2, 3. So the slope of this line is -1/3. It's negative, right, because it's going down to the left. Sorry, down to the right. And then the inverse, of that, let's actually make that perpendicular bisector. Click on that line. So this is the line I want. So we know that it's going to have a slope of, what's this? This is, a slope of 3 over 1 now, right? We're running 1, and we're going up 1, 2, 3, which is what happens when we take the negative reciprocal, right? We take our number -1 or 3, we flip it to get our perpendicular slope, which will be 3 over 1, but positive, right? Because a negative of a negative becomes a positive, and that just works out to 3. Okay? So again, we have to find our midpoint of AC. So we're going to go to our midpoint formula again, except this time, oopsies, sorry. So I had the wrong subscripts. So we're going to go AC now. So we're going to plug in our points, AC, 0, 3, and 5, 4. So that's going to give me 3 halves and 9 halves. Does that make sense? Let's take a look at the graph here. So the midpoint here that's going to be x. That looks like, it's a half, and this is going to be the middle of 4 and 5. So it's going to be 4.5, 1.5, which is what we got here, 1.5, 4.5. Now let's plug those into an equation here. So y is going to be 9 halves. The slope is going to be 3 from our original calculation. The x is going to be 3 halves. I'm going to plug all that in. 3 times 3 is 9, so this is going to work out to be 9 halves. So for 9 halves equal to 9 halves plus something, the only thing that will make that true is 0. So then I have my final answer. Y equals 3x. Does that make sense? That the slope of the perpendicular bisector of the chord AC is 3x? Let's take a look. So this is my chord AC. This line here, nope, let me sec. So this line here, this orange line, is the perpendicular bisector of AC. And it goes through 0. So the y-intercept is 0, and its slope is over 1 up 3. See that? Over 1 up 3. So y equals mx plus b, so that's going to be y equals 3x plus 0, or just 3x, which is what we got here. All right. So I know there's a whole bunch of these questions involving perpendicular bisectors and stuff, and I don't think I really took enough time to talk about this, because this is a very common mistake that everyone's making here, where we forget to take the negative reciprocal. So if we have a slope, to get the slope of the perpendicular line, we have to flip it. We have to flip the fraction. If it's just a number, we put it underneath a 1, right? If it's, let's say the slope, for example, is 4, let's say. A perpendicular slope of this is going to be 1 over 4, but then negative. Okay, so we flip the fraction and we make the whole thing negative. If it's already negative, it becomes positive. Okay, and then for it to be a perpendicular bisector, we needed the midpoint, we needed the middle. We can actually construct that here. We can just take this, we go construct. Where is it? Midpoint here. So all we have to do is we click on this line N here, and it came up with this point A. And if we click on the calculator, actually, let's make this a bit bigger, it'll show us the value here of the midpoint is 1/5 and 4.5. 3 over 2, 9 over 2. Okay, so it all worked out nicely. Okay, so that was a pretty long problem, very similar to one of the assignment problems. Just so you know, assignment number 5, or lesson number 5, assignment. You may want to watch this video again. All right? Okay, so best of luck, and hope you're all staying safe, and I'll be talking to you later.